All right, AUB students, welcome to a super fast crash course for PHYS 210. If you've ever felt like you're just drowning in a sea of equations, this one's for you. We're going to flip the script and look at this entire course not as a checklist of things to memorize, but as one single story. Okay, let's jump right in.
First things first, let's just get it out there. PHYS 210 is tough. We all know it. It's a huge hurdle, and the pressure is on, especially when you're trying to balance it with everything else and, figure out your future. And we see the conversations you're having online. For so many of you, whether you're on the pre-med track or in engineering, the stakes feel incredibly high. A course like PHYS 210 can honestly feel like this giant gatekeeper standing between where you are now and where you want to be.
And when you look at the syllabus, it's pretty easy to see why. Your head starts spinning, right? You're jumping from force and motion one week to the kinetic theory of gases the next, then suddenly you're doing waves. It's a ton of material, and trying to see how it all connects can feel, well, impossible.
But what if I told you that was completely the wrong way to look at it? What if, buried under all that complexity, there's actually a really simple, elegant story about energy? A story that you can unlock with just four fundamental equations that solve almost every problem in this course. So, our story starts at the very beginning, with the fundamental rulebook of motion. This is the law that dictates the why and the how of everything that moves. It's basically the cause and effect engine of the universe. And at the heart of that rulebook, of course, is Newton's second law, F equals ma. This is the most direct tool you have. If you can figure out every single force acting on an object, you can calculate its exact acceleration and map out its entire journey, moment by moment. So, think of F equals ma as the official rulebook of motion. It's incredibly powerful, but it's also incredibly detailed. And that's the catch. To use it properly, you have to account for every single force at every single moment along the object's path. That's a lot of bookkeeping. So what happens when things get messy? When the forces are changing or the path is some kind of crazy curve? Following that rulebook suddenly becomes a total nightmare. We need something better, a more big picture way of looking at it. We need a shortcut. And here it is. Enter the Work-Energy Theorem. Instead of tracking forces every single second, this amazing principle connects the work done by outside forces, like friction or air resistance, to the total change in the system's mechanical energy. It completely shifts our focus from the messy details of the journey to the simple final result. This is your ultimate problem-solving shortcut. It's like taking a before and after picture. All the complicated stuff that happens in the middle, the twists, the turns, the changing forces, it all gets bundled up into that one number, work. And just like that, problems that seemed impossible are suddenly totally doable. And this really shows you the two main strategies you have for any mechanics problem. You can either pull out the detailed rulebook and analyze the motion step by step, or you can use the super efficient shortcut and just compare the energy at the beginning and the end. Knowing which tool to use is half the battle. Okay, now let's zoom out, because the story of energy is so much bigger than just blocks sliding down ramps. It also governs the invisible world of heat, temperature, and the internal energy of things, like a gas trapped in a piston. And that brings us to the first law of thermodynamics. Now here's the big secret. This is just the work-energy principle wearing a different costume. Seriously, it's still just a statement about energy conservation. The change in a system's internal energy has to equal the heat you add to it, Q, plus the work you do on it, W. Same idea, different terms. Now check out this PV diagram. This is the exact kind of thing they love to put on AUB finals, and it can look pretty intimidating. But all it is, literally, is a picture of the work being done. That W in our energy equation, it's just the area under that curve. That's all it is. So the key is to think of this law as the universal energy budget. Energy is like a currency. It can't be created out of nothing, and it can't just disappear. You can only deposit it into a system as heat or withdraw it from the system as work. Every single process we study has to follow this budget. No exceptions. Okay, so we have our universal energy budget, but to actually use it, we're missing one last piece of the puzzle. We have to be able to describe the thing we're studying. If we're dealing with a gas, how do we define what condition it's in or what state it's in? That's where the ideal gas law comes in. PV equals nRT. It's this beautiful, simple equation that links the three big properties of a gas: its pressure, its volume, and its temperature. If you know any two of them, you can always find the third. It gives us a perfect snapshot of the gas's state.
You can think of PV equals nRT as the gas's state ID card. And why does that matter so much? Well, because for an ideal gas, its internal energy, that's the E-int from our budget equation, depends only on its temperature. This ID card tells you the temperature, which means it gives you the final key you need to unlock the entire energy budget.
So let's put it all together. Let's see how these 4 ideas build the complete story of PHYS 210, connecting everything from a simple falling block all the way to a complex heated gas.
And there they are, your 4 master keys. And together they tell one single story. You start with the very detailed rulebook of motion. Then you find the powerful shortcut of energy. After that, you expand that shortcut into a universal budget that works for heat. And finally, you use the state ID card to know exactly what system you're working with.
That is the secret to this course. It's not about memorizing dozens of disconnected formulas. It's about deeply understanding these 4, and more importantly, seeing how they talk to each other. Your success comes from seeing how mechanics and thermodynamics are really just 2 sides of the same coin.
So as you're getting ready for your finals, don't just see these as equations on a formula sheet. See them for what they really are. They're the fundamental operating principles of our universe. For all the future engineers and doctors out there, these are the tools you're going to use to understand, to design, and to build the world. So the only real question left is, what are you going to build?